Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Noémie Globus with us today. Hi, Noémie.
Hi, Frank. I'm super happy to be here.
Well, I'm super happy you're going to talk about this very awesome treasure paper. It's very nice. And Noémie, where are you located these days? What's your geolocation?
I'm Santa Cruz, University of California, Santa Cruz.
Very nice. And it is April 12th of 2023 as we record this. And is spring in full bloom there in Santa Cruz?
Yes, we have flowers and trees.
You definitely have trees, big ones.
What about Arizona?
We have no big redwoods. We have saguaros, but they don't quite get the same size as redwood.
But do you have flowers in the desert?
It's the desert's in full bloom right now. So we've got yellow flowers and purple flowers and orange flowers. We've got these big wasps that are coming out right now. They're huge. They're like 2 or 3 inches, and their thorax is so heavy that they sort of fly in like an L. They're flying like as they go along. It's hilarious to watch. It's really cool. Very cool. And what is that amazing molecule over your middle of your head there? What is that?
So that amazing molecule is a DNA molecule.
Cool. Very good.
Yeah, which is related to what I'm doing right now in research.
Very cool. All righty. And Noémie, what do you like to do for research?
Okay, so we're coming to it. So for a decade, I have been doing high energy astrophysics. And I'm mostly interested to know what are the sources of ultra high energy cosmic rays, which is what we are going to talk about. And it has been a 60-year-old mystery. But now I'm becoming more and more an astrobiologist.
Okay.
I'm interested to know what could have been the role of cosmic rays in the origin of life. And this is why you see this DNA molecule behind me, because DNA has a particular property that it's shared in all living organisms, that the sugar in DNA are chiral, meaning that in reality, they could come in 2 sets of mirror images, like my hands. This is the word chiral comes from hands in Greek. But DNA, for some reason, choose to use only the high-trended sugars. And if we understand how life made this step, this very particular step of using only one mirror images than the other, we could understand more how life form and which are the astrophysical environment that could be prime target for the search.
Very nice.
Thank you.
And before we get into the article itself, I think we're going to do a little 4-slider on B. So go ahead and put your slides up there, Noémie. All righty, and there you go. Let's do a 4-slider.
Yeah, so the paper we are going to talk about deals with cosmic rays that are charged particles, and because they are charged particles, they're going to be deflected by galactic and extragalactic magnetic fields that are poorly known. So we are inside our galaxy, so it's very difficult for us to understand how the galactic magnetic field look like. But what we can do is that we can observe magnetic fields in galaxies that are similar to the Milky Way, like this beautiful one that you see on the screen.
Beautiful.
And you see that there is a very large-scale magnetic field. And with Faraday rotation measurements and synchrotron radiation, we are able to actually reconstruct the galactic magnetic field of our own galaxy. And this is the model we are using in the paper, mostly. There are 2 models, but this is like the most state-of-the-art model, the Johnson and Farrar 2012. So you can see it here. And this is what we are using, cosmic ray physicists, to model the propagation of cosmic ray in the magnetic field. And the magnetic field intensity in our galaxy is of the order of a microgauss. So at the highest energies that we observe, 10 to the 20, 10 to the few times 10 to the 20 electron volts, the Larmor radius of the cosmic rays is larger than the size of the galaxy. So this is a hint to their origin. It's likely to be extragalactic because we do not observe strong anisotropies.
Okay.
And this is the cosmic ray we are going to talk about, the ones that are the less deflected.
Yes.
And just to give you an order of,
I love that picture.
yes, number that is impressive, 10 to the 20 electron volts cosmic ray produce over 100 billion of particles in the atmosphere. It's a very hard rain. This is from the Pierre Auger Observatory website. You can see here a muon tank. And we can reconstruct the arrival direction quite well. The uncertainties of the order of a degree on the sky. So this is why we were interested to study this extreme energy cosmic rays. So cosmic ray around 150 EeV. So EeV is 10 to the 18.
Yep.
So, and this is what we are going to talk about.
Very cool. Thank you for that background. And let's go ahead and take a look at this very awesome APJ article. It's open access, people. You can go get a copy for free. Go grab one. Treasure maps for detections of extreme energy cosmic rays. And Noémie, take us away.
Thank you. So yes, so first let me acknowledge my co-authors, Anatoly Fedinich and Roger Blandford. Anatoly is in Academia Sinica in Taiwan, and Roger is at Stanford University. Okay, so as I said in my intro, we don't know the sources of cosmic rays. It's a mystery we would like to solve. So this paper is, so it's called Treasure Maps. So as I said, cosmic rays are deflected by galactic and extragalactic magnetic fields. But we are able to reconstruct quite well the arrival direction of cosmic rays, studying the air shower. So this shower of particles I was showing that are produced when the cosmic ray interact with the atmosphere. So there are two current experiments, one in the north and one in the south, that are observing ultra high energy cosmic rays. So Telescope Array in the north and Pierre Auger Observatory in the south. So there are two important results that were confirmed by the experiment is that at the highest energy, the spectrum of cosmic ray shows a cutoff.
Okay.
This was predicted in 1966, 2 years after the discovery of the CMB, the cosmic microwave background. So the cosmic ray at the highest energy interact with the CMB and will produce, if there are protons, they will produce pions. So this will limit the size of the cosmic ray observable universe to a few hundred of megaparsecs for protons. For nuclei that are heavier than protons, it's a bit more complicated. So they also interact with the CMB by processes that are called giant dipole resonances and also pion production. So this will also going to limit the size of the cosmic observable universe for nuclei. But nuclei, contrary to protons, can also photodissociate.
Yes.
It means that if you have a source of ultra high energy cosmic rays, the energy spectrum and the composition at the source will be different from the energy spectrum and the composition which is observed on Earth.
Yes.
And since we don't really know, because these cosmic rays are at energies that are orders of magnitude higher than what we can do in human-made accelerators, right?
Yeah.
We can only extrapolate cross-section for particle interaction, so we don't really know the composition at the highest energies.
Okay.
We know that iron could propagate more or less hundreds of megaparsecs, that it will be the same horizon as protons. But as you outlined here, CNO intermediate mass elements are more fragile Helium is very fragile. So if you have a cosmic ray helium detected at 10 to the 20 electron volts, you know that it can only come from our local group of galaxies. Because we know it would have photodissociated on its way by the interaction with the cosmic microwave background photons. So what we did here to do these treasure maps is that we know that the distribution of galaxies around us is anisotropic. We have beautiful galaxy catalogs, right? We know we have the Starburst galaxy catalog, the catalog of radio galaxies, so we can actually have the distances, right, to each of the putative host candidates, right?
Yep.
And we can calculate the GZK horizon for different energies and calculate an attenuation factor, right? Because if you have a source which is at 10 megaparsec, the cosmic ray will be less prone to this interaction, so they will be less attenuated than if you have a source at 20 or 50 or 100 megaparsec away.
Okay.
Till it's not observed anymore, right? Because until you cannot observe because it will outside the GZK horizon.
Yeah.
So I hope I was clear.
I'm with you. I'm with you. We're good. We're good.
Okay, so what we did in the section 2 is we actually run a code called prints to derive the GZK horizon for different distances, and we ask ourselves the question: since we don't know the composition, we cannot observe, we cannot derive the composition of an event by event basis right now, as I said.
Right.
So we ask ourselves the question: if we had mass sensitive detector,
that would be cool.
Would we like do a tomography, right, of the universe? Because we would know, because we know the photodisintegration distance, right? We would know at which distance the source would have to be. So just to give you an example, if you have an iron nuclei detected at 310 to the 20 electron volt, and you know it's an iron nuclei, you would know it cannot come from Virgo cluster, for example. But if you know it's a proton, that you know, oh, this is still a candidate source. So that's the idea behind this section.
Got it.
Yes, so if you go to the maybe I will not, I mean, the equations are straightforward. We derive like attenuation factor due to these interactions.
Yes.
And we consider two energies, 150 EeV and 300 EeV.
Okay.
And we neglected the extragalactic magnetic field because it doesn't have a strong effect on the horizon at these energies.
Yeah.
So we defined here an observable mass and observable energy. And I mean, if you look at equation 3, there is the attenuation factor depends on the mass and energy at the source distance, the spectral index, and then we ask ourselves the question, what is this attenuation factor for a given observed energy and mass? So if you go to the figure, I think it will be maybe clearer if I describe the figures. Yes.
Here we go.
So in the top panels, you can see that this is for an observed energy above 150 EeV, but there is no mass sensitivity, meaning that it could be A ops is greater or equal to 1 to protons. So if you detect a cosmic ray, it could be proton to iron, right? You don't really know.
You're right.
And so it means that if a source is giving you iron and we detect a proton, it could come from an iron source that has photodisintegrated on the way, or it could come from a proton source. We don't have a way to distinguish between them.
Yes.
And the attenuation factor, you can see very close to us is 1, right? It's not attenuated. But here the arrows shows you where 95% of the cosmic ray come from. So this is like the horizon. Right. And it's the different colors are for different masses. So you can see that for all hydrogen, intermediate, and heavy nuclei, they all come from our local supercluster, which is of the size of 40 megaparsec, more or less. So this is the size of our local supercluster, right? Now, if I have a composition sensitive instrument, and I can detect, and I can say if I detect a cosmic ray, I know it's a carbon or heavier, which is the lower panel. Then I know that it couldn't have traveled for so far, because if not, it would have disintegrated on the way. So you can, it's really limiting the size to the local group of galaxy. But iron is not so fragile, so it still have horizon of 40 megaparsec or so. So that was actually interesting to show that really, if we in the future would have this possibility to understand what is the composition on an event by event basis, we could really, first, we would be able to actually understand better the propagation in the galactic field, because the Larmor radius depends on the charge, as I showed.
Yes.
But also to know the distance traveled, right, from the source.
Very nice.
And then figure 2, I will not repeat, it's just the same, but for 300 EV.
Okay. And so, we get the same.
Yeah, the horizon is just smaller, but not so smaller for protons. For iron, it is. So you see that I was saying it couldn't come from the Virgo cluster, which would disregard sources like cluster accretion shocks. But 3.2 megaparsec, I mean, Centaurus A is at 4 megaparsec away, right? So it's still more or less possible to come from a radio galaxy. But if you really, you know, I mean, above this distance, if you observe CNO elements, then it could be something which is very local, a transient in our local group, or even in our own galaxy. So gamma ray burst, or all these source candidates, the goal would be to really know if there is a way to actually, you know, distinguish.
Yeah.
Oh, yes, that's
cool.
that's
I'm with you.
Okay, so that's one calculation we have to do for these treasure maps.
Yes.
Then now we have this attenuation factor. We have to deal with the propagation in the galactic magnetic field. So what we do is that we say, okay, we have the catalog of galaxy around us with distances and positions.
Okay.
Then when the cosmic ray would travel from this, so if you have a transient in one of those galaxies, the cosmic ray will travel to us, and then I will encounter the galactic magnetic field.
Yes.
So they will be deflected, first of all, because of this complex structure. As you saw, there is like a large-scale poloidal field, there is a large-scale toroidal field too. So it's actually like lensing. Like, it's really like lensing. So if you imagine a sphere, sphere around the galaxy, imagine, and some source could be magnified and some source could be demagnified, exactly like, you know, lensing of light by but this is, so according to Liouville theorem, right, you consider phase space. So for a purely isotropic sky, you should have a purely isotropic flux on Earth, but the sky is anisotropic. The distribution of sources is anisotropic around us. So this, if you have a model of a galactic magnetic field, you have this lensing effect, which is characterized by M, which depends on the galactic coordinates L and B. So this is what you see in the, step in the, if you go a bit up, it's like 10 lines above equation 5. So we are explaining that we have the K, which is exactly, thank you, the attenuation factor, but we also have to take into account the fact that a source could be magnified or demagnified. So this will change the flux, right?
Indeed.
So,
yes.
so if you say I have a source which with a given energy, which is a U ISO, so the isotropic equivalent. This is your yield in cosmic rays.
Yes.
If you want to observe doublets and to put a constraint on the doublets, you have to take into account the effect of the GZK attenuation and also this magnification factor, which will come in the equation 5.
Yes.
And another thing is that if you have a transient source, you don't only have in the galaxy an ordered magnetic field, which has a lensing effect, you also have turbulence. So I haven't talked about this, but this is very important because cosmic rays will scatter. So they will diffuse. So there will be a delay in the arid time of cosmic rays, because if they enter zones of more turbulent magnetic field, like the disk of the galaxy,
right,
there will be a delay, which is in equation 5 given by this tau d.
Yes.
So imagine you have no magnetic field and you send a bunch of cosmic rays, you will receive them at the same time. But now they are entering the galaxy, so they will travel in slightly different trajectories due to the scattering. It's really like scattering, it's like diffusion. And then you will have time delay distributions. So, so a transient source will give you a pulse, and the pulse will be enlarged if the turbulence is stronger. So we have to take this into account also in this equation for what is actually the needed energy, isotropic equivalent energy in cosmic ray to give you a doublet. So, okay, so that was very long, but this is what we are doing here.
No,
so
but it was clear, so that's good.
Yeah, so for each, okay, so for each galaxies in our catalog of galaxies, for example, Cenae, we would know that if you have a transient there, we know where Cenae is. With our galactic magnetic field model, we can calculate the magnification factor.
Yes.
We know the attenuation due to the GZK.
Uh-huh.
Let me just close, maybe, no, they stopped. Sorry, there is noise. But so we can calculate for each of the galaxies this U ISO to get you a doublet. So then we go to the source catalog, which is the next section, and we are just here explaining what we are going to use, right? So we use the all nearby galaxy catalog, et al., and we also have Van Wenzel catalog for jetted AGNs.
Oh, yeah.
The Lunardini catalog for the starburst galaxies. This is a good source candidate. People are in the community really talking about this right now. Yeah. So we choose this catalog, and if you go to the next figure, you can see that to illustrate, yes, figure 3, you can see on the top the source candidate within 2 megaparsec, 5 megaparsec in the middle, and 40 megaparsec, which is the size of our local supercluster, and the GZK horizon, as I was showing, at 150 eV for iron and protons, right? So you can see this is the distribution of the galaxy around us.
Very nice.
And colors are for, so yellow is for the jetted AGNs, the big dots are for starbursts, and the small purple dots are for the all local galaxies, including the dwarf galaxies. So, and the galactic anticenter is in the middle here.
Yes, there's M87, Cenae, NGC 253, M82. Very good. Okay, I am with you.
Okay, so if you have a transient that give you cosmic ray, extreme energy cosmic ray doublets, these are the host candidates, right? So we are taking these catalogs, and we want to calculate the number of doublets if the transient has a given energy. So since we don't know what are the sources, we will span all the possible energy for transients, right? From 10 to the 47 R per second luminosity to 10 to the 52, because these are like the most powerful gamma ray bursts, right? That give you a yield into...
Including recent ones, yes.
Yes. And yes. And So what we are doing, so we need to calculate this galactic magnetic field delays, because this is what was important, right? This is what is going to dilute your signal. So as I was showing in equation 5, this enter into yes, thank you. And then also M, which is a magnification or demagnification factor.
Yes.
So for each of the sources of the catalog, we are going to do this, as well as the GZK attenuation, because we know the source distance. So from section 2, I showed you that we run this code to calculate for each distance what would be the attenuation.
Yes.
So basically, we can tell you what would be the requirement in terms of energetics to get a doublet from a transient at a given energy from this source.
Gotcha. I'm with you.
So that's the treasure maps.
Good.
So yes. So this is
the plan for the treasure maps.
Yes, it's
We'll get
like
to the treasure maps.
Was. Okay.
Okay.
So we are getting to the treasure maps. So to calculate the delay, I mean, this is explained in this section, right? And we have to make some correction, which is shown in figure 4 to really calculate the delay, because we are considering a sphere. So that's important for people that are really doing this and are curious about how we did it, but we took everything into account. And so we have actually the distribution of time delay for every pixel on this sphere, right? So if we have a source in a given direction, we can relate to an observed direction on Earth. So if a cosmic ray is detected in this direction, for example, if you see what I'm pointing out,
that way.
Back propagation, which is shown in this figure 4 on this purple line, we would know the direction of entrance in the galaxy. So the true direction, which would point to the true source, right? So and we would know the time delay that we have to phase correct. So what we did is that we sent cosmic ray in all possible direction in the sky. We send like the 8 trajectories, and for each pixel of arrival direction on Earth, we have like a number of cosmic rays from a given arrival pixel on the sphere. So we can calculate the magnification and the magnification and the time delay for a given extragalactic source.
Okay, nice. Okay.
So,
all right.
Okay, so let's go to the next figure then, maybe.
Let's see. We talked about that. And here's our first treasure maps.
Yes. So this is what we get. So the left panel is, we have also, of course, to take into account, I haven't said that, sorry, the field of view of the detector. So we have 2 instruments, right? Because I mean, we have sources like the maps of the source candidates I was showing you, the galaxy catalogs. They are full sky maps, but on Earth we don't have a detector that is able to observe the full sky.
Sure.
Telescope array has its own field of view, which is smaller than Pierre Auger. And this is what you can see here in the maps. The white zones are the zones that are not observable. Exactly. Because Pierre Auger is in the south, so it cannot observe
everything.
And telescope array is in the north, and it's smaller than Auger, so it cannot observe a lot of sources. So these maps are for protons. So let me go a bit, let me describe a bit the maps. So the top is for one model of galactic magnetic field. The bottom is for another model. So this is why you see GF12 Planck on the top and TF17. So these are 2 different models of galactic magnetic field. The one I was showing in my introductory slide is the one on the top.
Yes. And
the time delay in the galactic magnetic field are figured in colors. Exactly. So this is in log. So from 10 years to 100 years in green to 10,000 years in red, right?
Alrighty.
And you can see that for protons, the time delays are quite small, like less than 100 years in this direction. So This is, yes, from many galaxies. For example, M82,
Okay.
which is this scattered, just, I mean, if you scroll up, or yeah, actually, if you scroll down, sorry, it's indicated in the bottom panel.
M82 is right here.
Yes, so you can see it's
So
purple.
M82 is right about here.
Yes.
That cluster.
So, exactly. So it's a few megaparsec away, and you can see that the time delay in the extragalactic magnetic field is negligible. Here it's 0.1 nanogauss. And then when it enters the galaxy, it will not suffer a lot of deflection. So it still stay very small. So if you have a transient source like ejecting a lot of cosmic rays into our direction from M82,
Okay.
the time delay between the first cosmic ray you detect from this source and the latest cosmic ray you detect would be of the order of 10 to 100 years, which is what you can see in the color of the maps.
Okay.
So these maps take into account also the GZK, so you can see the transparency. Some of the sources, yes, close to the galactic anticenter actually are not in full color. This is taking into account the attenuation of the flux.
Right, right.
Effect.
What is the essential difference between these two models from the JF12 Planck and the TF17? What is one of the essential differences of those models? Is it the strength of the field? Is it the directions?
So
So
all models, yes. So there are different assumptions for the turbulence. For the TF17, actually, there is no turbulence. So you can see that
got it.
there is like a strong lensing, which you can see by this sharp edges. Yes.
Yes.
While in the GF12, since you have turbulence, then it's more, yeah,
I'm with you.
It's more blurred. Yes.
Okay. Thank you.
Okay.
Good. Thanks.
Also, the order is not the same, but yes, we wanted to show two models, and it's not so different from the time delay. So that was what was important for us.
Okay, good.
Yes.
Robustness.
So now you can see that for protons, because they are not so much deflected, right? Protons, the rigidity of proton is the same as energy, since the charge is 1.
Yes.
So this has the highest rigidity particles, so they are the less deflected particles.
Right.
For the same energy, if you look at the sky map for iron, you will see something interesting. So
Iron.
Same energy, yes.
Ooh.
Iron would be more deflected.
Ooh.
And the rigidity of iron, right, is 150 divided by 26 for this map. So you will have access to, since it's 26 times less, you can have more deflection, and you can have access to part of the sky that is outside the field of view of the instrument. So you can see it very well on actually the right hand, which is for Pierre Auger Observatory. Yes, this one. Pierre Auger can observe in this, if you remember from the previous plot, there is a patch in the sky, yes, that Auger cannot observe, a white patch.
The white areas.
Yes, exactly. M82, for example, is not observable by Pierre Auger. But if you are an iron nuclei from M82, you have a chance to be deflected by the galactic magnetic field and to be observed actually both by Auger and telescope array. So that is very interesting, and that shows you how important it would be to have an instrument that is able to say, this is a proton and this is an ion on an absolute basis. So it's actually the same. So the sky maps are like illustrative, right? So to be quantitative, what we did is that we use this magnification factor, time delay, which are figured in colors here, and attenuation due to the GZK effect to calculate this U ISO, the energy to get a doublet, right? Yes. And then we assume transient for any energy. So this is the plot. I think it's the next plot.
Yeah, I think that. So I think that. Well, this is for nitrogen.
Yes, that one was for nitrogen.
And
So actually, yes, if I can say one word about that one.
yeah, sure. Nitrogen's fun. I
You
like
can
it.
you can see that you have less points just because you have less candidates because of the GZK.
Yeah.
Because the intermediate are very fragile again, so you only have very close by galaxies.
Yeah. Okay.
So
Okay.
to come back to the number of doublets that you can observe, so
Yes.
take into account the magnification and demagnification factors. What we did is that we calculated the time delay distribution. So if you go, please, to figure 9, that is a good figure to actually illustrate this. So I will first explain this one.
Very nice. Okay, I'm going to do a global and we'll zoom in as need be on figure 9 since this is the money shot. Okay.
So the sky map shows you, so this is for the GF12 model corrected by Planck, so updated by Planck data. And you have illustration for few sources, one in the Galactic ANSI Center, one SENEI, M87 and M82.
Yes.
And you can see that there are two effects here. For example, if you compare M82 and M87, you can see that one is like, for M82 is just the turbulence. So basically you are going to have a spread of the signal, right? You are sending a pulse of cosmic ray toward Earth and it's going to be spread, like a Gaussian spread, just and it's less spread for 300 EV than for 50, which are the colors. But for M87, you see that you have a strong lensing effect. So spread, the blue is of course more spread than the green again,
Very
but
good. Very
you
good.
also have the lensing. So if you now do the time delay, it's not just, you know, like if you do a time delay, you have to take into account this magnification factor. So that was the important thing. So and the examples that are here are shown for the different rigidities in different colors in these distributions. So you see that you have a mean of the time delay distribution. And of course, you have more that arrive at later time that arrive at earlier times. So the distribution has a skew. And the time delay, the mean is, of course, yes, larger, like for higher and higher rigidities. So at 150, if we follow this example for M87, at 150 exavolt rigidity, so like a proton at 150, the mean time delay is 10 years or so, right? But for 50 is something around already 70.
Right, pretty big effect. Okay.
So using this time delay, we are using this time delay distributions to be able to calculate the U ISO that I was showing in equation 5, and to calculate the number of sources. So this is the previous figure, figure 8. So yes, so this will tell you from this consideration. So on the x-axis, you have the U ISO, which is the energy you put into cosmic rays.
Yes.
And the exposure of the detector. So on the left, it's for telescope array, and on the right is for Pierre Auger Observatory. And we choose any energy, as I said, for the transient because we don't know. So it's a model. We assume there are transient sources of extreme energy cosmic rays from 10 to the 40 to 10 to the 52. ERG in cosmic rays, and they are distributed like, for example, all local galaxies. So that was the catalog all local, which was the purple little dots, right? And we know from each of the galaxies of this local catalog the distance. So we know the attenuation, and we know also the magnification factor and this time delay, which I'm showing you, right? For example, for M82. Or, so then we can calculate for every U ISO the number of host candidates for doublet. So you can see that these are the number of galaxies that satisfy the condition. I have enough energy if I am a transient at 10 to the 49 to get a doublet of cosmic rays.
Yes.
Of extreme energy cosmic rays, which is what would be interesting, because if we detect doublets in the future, then we might be able to say, oh, this could be a transient source, and if this direction is giving us M82, then we know that the transient should have this 10 to the 50 erg energy in cosmic rays, and then you can distinguish between different source candidates.
Cool. Very
Sorry,
cool.
that was maybe a bit complicated, but so
Cool.
on the, yeah, okay.
I'm
So
good. I'm with you.
let me know if yeah, I should give more details. But yeah, so these figures are for the different catalogs. So the purple is all local, the orange is starbursts, and the yellow is radio and jets. And as you know, we don't have a lot of jetted galaxy, like you saw on in our local universe. So this is why you see we have only one candidate, for example, for proton and the transient energy, the flare in cosmic ray should be 10 to the 50 erg, more or less, to be able to observe a doublet. But if you have a gamma ray burst occurring in a white dwarf, so the rate of gamma ray burst is pretty low, but then you can see that for all local in the TA sky or in the PAO sky, the 47, you have already 100 galaxy candidates to satisfy this energy criterion. So yes, so the last part, which is also a bit, it's a lot of equations, but it's actually simple to, just before the hotspot actually, is to say that if we were able to actually, so we observe hotspots, and I will come to this. So a bunch of cosmic rays that are clustered around a certain direction. But we know the energy with some uncertainty. It's 15% uncertainty for telescope array and a bit less for Auger. But the thing is that we don't know the mass.
Right.
But if we knew the mass, I'm always coming to this, we will know the rigidity. So it will be awesome, because we would know, we could like actually order the events and say if they could come from a transient or not, according to this time delay distribution, because we would know that higher rigidity have to arrive earlier, right? So if you see a hotspot of cosmic ray in the sky, if it's a continuous source or if it's a fluctuation, it will not show this ordering, right? But if it's a transient source that give you a spectrum of cosmic rays, then the highest rigidity ones, like you can see on these plots, have to arrive earlier than the lowest rigidity ones. So if we had access to this information, we could say, oh, this would be the signature of a transient. Cool. So telescope array observe an hotspot. So just to play with this, we actually did the treasure map for this hotspot. Cool. But fortunately, we don't have the info on the mass. So that was the section illustration on the TA hotspot, which is after this one.
Case of the TA hotspot.
Yes. So this telling you that we observe like 20 events above 57 EeV. Okay. And since we don't know the mass, we did it for all possible rigidities. Sure. So we did the same, and we actually calculated again the time delay, and we see that this hotspot, which is nice, is located in a magnetic window of small time delay. So if you scroll to the treasure maps, I think they're in the, there is one here. Okay. One here. So you can do the same exercise. You can see that the very close galaxy like M82 and there is another starburst have a small time delay. They will be in blue. Yes. And if there was a transient in these galaxies, this could be responsible for the TA hotspot. For the 20 events we observe, because we could actually be observing the tail of the distribution of this time delay between events. And we did the same exercise. We asked ourselves a question. Now, not for a doublet, but for 20 events, what would have been the required U ISO during this 12 year of TA operation to give us the TA hotspots? And you can see the candidates. So you have like 10 galaxies at 10 to the 49.
Yeah.
So, and we were talking about the implication, what kind of sources can give you 10 to the 49 erg in cosmic rays. And this is what we discuss in section 10. So, because of course we have a number of galaxies, but what about the rate, right? Because if a source is very rare, less than 10 to the -4 per year and per galaxy, then it's hopeless in 10-year observation period, right? Even if it's a closed source. So this is our last discussion, like what would be the implication of observing doublets? And then we don't really know the rate of like tidal disruption events. These are poorly constrained. We know the rate of gamma ray bursts, low luminosity gamma ray bursts are low luminosity, but they're higher rate, like 100 times the high luminosity ones. So this is the discussion here, basically. We could, So
very cool.
So yes, to conclude, this is a paper saying basically that really if we could have access to more information about the mass when we do cosmic rays, we could actually say
lots.
If we observe again, like if a source could be a transient source.
Yes. Oh, that's even better.
Because if it's a transient, it has this specific signature in arrival time.
Right.
Also, continuous sources like cluster accretion shock might be outside the GZK horizon for iron at more than 200 EeV. So, take-home message for the cosmic ray community is we should really work on improving the way we can obtain the information on the composition of the events. So, yeah.
Lovely. Absolutely lovely. And if you get there, people, there's 2 appendices. I'll leave those to you to take a look at. And Noémie, I want to thank you so much for walking us through this very lovely treasure map article. Very cool. Thank you.
Well, thank you very much for inviting me to talk about it.
Sure. I'm not going to let you off the hook quite yet. So you did mention it several times, and I just want to push on it a little bit. So where do you think we go with this topic over, let's say, 2 to 5 year timescales? Are there additional theoretical models that could be run? Do we need to do a larger parameter study, maybe with different bees or different catalogs? What is the state of the, and I don't mean to put you on the spot here, I'm just asking a broad question. What is the state of detectors to be able to tell what the mass is? Right? Are there efforts going on in that direction, or just where do we head over the next couple of years on this?
Okay, so as I said, since we cannot access to this energy at LHC, to extrapolate the cross sections. So in the cosmic ray community, we are using 3 different hadronic interaction models. This is to derive the composition, and they do not agree with each other.
Cross sections, yeah.
So I'm not like a nuclear in this hadronic interaction, but I think there is an effort that is being made right now to understand what are really the differences, and to address a problem which is called the muon puzzle. I don't know if you heard about this, but
go ahead.
For all of the models that we have, the models they under-predict the number of muons that is observed. And muon is also an observable for the composition. So I haven't said that. So there are 2 observable. There is depth of the shower maximum, that like protons are more penetrating. So for a given energy, if you can measure this atmospheric depth, you are able to say this is more a light element than a heavy element, but also heavy nuclei will produce more muons on ground. And the number of muons that is observed is in excess of what is predicted. So this is called the muon excess problem.
Mhm.
So this is one thing that is addressed by the community to better understand the composition. I know that also radio can tell you something about it. So there are antennas that are being put on the muon tank right now in Auger to better know the energy as well. And since the two instruments, the experiments use different instruments, telescope array use scintillators and Auger use muon tanks,
Right.
they are not calibrated the same way. So what is being done right now is that there are some muon tanks from Auger that are being put on the north to be able to cross-calibrate. So
Nice.
there's effort being
There's
made
motion.
to. But then if you're asking me like what after telescope array and Auger, I really hope it will be a full sky experiment like POEMA.
Okay.
Is I mean this is like at the stage of being discussed. I think right now, I mean, it's not sure that it's going to happen, but it's to observe a cosmic ray from the sky. Actually, you will be able to observe the cosmic ray with two satellites. And yeah, this is a probe to this called
next gen,
yeah,
right?
that would be really nice, because then we would have access to full sky and we will not have this problem of is the north and the sky intrinsically different because they're not, yes.
Right.
So but for the composition itself, to come back to this,
yes,
I think both in understanding better the physics of the shower, so maybe try to find other observable, like for example, if a shower of protons scintillate more in light than a shower of nuclei, or some temporal signature that would be different. I don't think this have been probed, and that would be really interesting.
Yeah, very.
Because it's like lightning, but it's like also spreading differently. So I think the sensitivity right now, it's not good enough to see these differences, but it could be in the future. So,
well, nice thing about this article is it sort of gives targets, right, for people to go after. Here's something you could go after if you did it. So it's very good. Has a practical aspect to it. Wonderfully. Very cool. Noémie, I want to thank you so much once again for spending some time and talking about your very lovely article. Very nice.
Thank you once again for inviting me. It was a pleasure.
And that'll do, everyone. And I hope this made your astronomy or astroparticle physics day just a little bit better. And we will see you on the next one. Bye-bye.
Bye-bye.